All right, here is this problem from section 4.5 that we didn't really get to finish in class. I started it, ran out of time to finish it, and just kind of talked about how to finish it. So I think it's a good problem because it has a lot of the stuff that's tricky about the stuff involved. And it also, I want to show off some of the things you can do with Sage to save yourself some work for this kind of thing. So, anyways, uh, let's get started. So first of all, we gotta see that the solution we're looking for, if we're trying to satisfy these initial conditions, is going to be some particular solution. Let's just call it y. And that y is going to be the result of doing some other particular solution plus a solution of the homogeneous equation, which is going to be something of the form c1y1 plus c2y2, where y1 and y2 are any particular solutions of the homogeneous equation, which is y double prime plus 2y prime plus 2y equals 0. So what we've got to do is, first of all, find y p, the particular solution of this equation, using the undetermined coefficients. And here that means finding the a and the b so that yp equals a times cosine t plus b times sine t. And I picked that because that's the general form of something when you have like something sine of t plus something cosine of t that we went over in 4.4. So then after you've got that, we're going to have to find our solutions of the homogeneous equation. And to do that, you want to use the auxiliary equation. You're going to find the values of r that make r squared plus 2r plus 2 equals 0, because we're again finding solutions of the homogeneous equation. And so you're going to do the tricks from section 4.2 and 4.3 where you do e to the power whatever r you get times t, and make that be your y1 and y2 functions. Or maybe use sine and cosine if you get imaginary solutions. Anyways, then once you got that, you want to find the C1 and the C2 that satisfy the initial conditions given here. All right, so let's get started by determining the coefficients here that will make a and make this work. So the y prime here is going to be negative a times sine t, that's a derivative of a cosine t, plus b cosine t, and then the derivative of that will be negative a cosine t minus b sine t. And we want to plug those into the original equation here in the place of the y and y prime and y double prime here, and so and see what a and b will be that can make this be the same function on both sides. So that's going to look like what we've got here, where we have 2 times y prime over here, y double prime here, and then 2 times y prime here, added up to hopefully get 5 sine t plus 5 cosine t. And to make that work, you need to make sure that all of the coefficients of cosine of t add up to 5 here. So otherwise, because we want to get the same function of t on the left and the right, so we need to the left side to also have a 5 cosine of t in it. So that means that negative a, this 2 times b cosine of t, and 2 times a cosine of t should add up to 5. So I wrote that here as this equation. Negative a plus 2b plus 2a equals 5. And then for the coefficients of sine of t, we want those to add up to 5 as well here. So that's going to be the b times sine of t minus 2a sine of t. That should be a minus here. Notice that mistake. Plus 2 times b sine of t is right here. So those are all the coefficients of sine that need to add up to 5. So you can write this as a system of equations and sort of with combined terms in the standard form, like negative 2a plus b equals 5, and this one gives you a plus 2b equals 5. And you could solve this using elimination or substitution. With a nice small system like this, it's totally fine to I think the easiest way is probably to just use substitution. Like turn this equation into b equals 2a plus 5, replace this b with 2a plus 5 here, and that equation is going to look like a plus 2 times 2a plus 5 equals 5. And if we solve that, and that gives you negative 1, 3 after solving it. So that's your particular solution is going to be negative cosine of t plus 3 times sine of t. So the problem with that, though, that is a solution of the differential equation, but it doesn't satisfy the initial conditions. For example, if you plug in 0 into that, you're going to get negative 1 times 1 plus 0, which is going to be negative 1, not 1. So it doesn't work there. So then we have so we got to get solutions of the homogeneous equation that we can possibly add to this. So to do that, we need to solve this equation here for r to see what the exponents of e should be in those exponential equations. So using the quadratic equation, you're going to get negative 2 plus or minus the square root of 4 minus 8 over 2, I think, which comes out to be negative 1 plus or minus I. So at this point, the main thing to do is you could do, by the way, the e to the negative 1 plus I all times t as like one solution. And say your y2 is going to be another solution, which would be e to the negative 1 minus I all times t. That works, except the exponentiation is weird. So yeah, dealing with the complex numbers would make this annoyingly sort of difficult. You could do that and you'll get the right answers, but you could, if you just want to get real solutions because you have real valued initial conditions, the trick from 4.3 is that you can get real solutions out of this by saying y1 equals so yeah, we're gonna skip that. So we're gonna get y1 is e to the negative 1t times cosine of t, and y2 is e to the negative 1t times sine of t. And we're using a 1 times t in each of these because it's like 1 times I there, but it's ugly to write that. And the negative t here is like the negative, oh sorry, that should be negative 1 times t here. That comes from the fact that this is negative 1 here. So those are two particular solutions, so two solutions of the homogeneous equation, these will make it so you will get 0 on the right side. So then we can put these together to get an overall solution that satisfies the initial conditions. So the general solution is going to be anything of the form something like this, where you've got your particular solution that we got from over here with the values of a and b, plus some multiples of either of these homogeneous solutions. And we need to see now what C1 and C2 should be to satisfy the initial conditions. So we're going to plug in, let's see, all the way up here, t equals 0 into this, but we also need to plug in t equals 0 into its derivative so we can get y prime of 0 equals 2. So we do have to figure out y prime here for that, which is going to be a little messy. This is what I got doing that nasty derivative. So first, with this part, you got to use the product rule. Doing the derivative of cosine becomes negative sine here first, and then also the derivative of the e to the negative t part, leaving the cosine alone, makes this part also become negative. Here, with the next one, using the product rule again, turning that C2 thing into these two things, and then I just did the regular old derivative of negative cosine into sine, and derivative of 3 sine should become positive 3 cosine of t. Whoops. And let's see. So now we want to plug in 0 into that to get into the original thing to get 1. That's going to look like C1 times e to the 0 is 1, cosine of 0 is 1, sine of 0 is 0, so that will be C2 times 0, minus cosine of 0 is 1, plus sine of 0 is 0. So in other words, this is just saying that 1 equals C1 minus 1, or in other words, 2 equals C1. So we're going to take that now. Well, whenever that means I can always just plug in a C1 equals 2 here. And for the next one, because we're going to plug in 0 into y prime, and y prime of 0 is supposed to be 2. So we want to get 2 as the result, and I'm going to be plugging this into y prime here. So I'm also plugging in 2 into C1. So it's going to be e to the 0 is 1 times sine of 0 is 0. So that whole thing is going to be 0 there. This part will become minus C1, which is really 2, times 1 times 1, plus C2 times 1 times 1, minus C2 times 1 times 0 here. It's going to be 0, plus 0 plus 3. So let's see. This equation is going to turn into 2 equals negative 2 plus C1 plus 3. That negative 2 plus 3 becomes positive 1. And you're going to get 1 equals, oops, it's supposed to be C2. It's a text message. And so you got C2 equals 1, C1 equals 2. It's like they took off a hat and like traded hats with it because their names are backwards. Anyways, that gives you the answer to the question, hopefully. Let's see, y equals 2 e to the negative t cosine of t, just replacing the C1 and the C2 now with their actual solutions, plus 1 e to the negative t sine of t minus cosine of t plus 3 times sine of t. Okay, so doing this all like this by hand is a good exercise in calculus and algebra stuff here. It takes a lot of work though. And there's a lot of ways to make mistakes. I think it's also important to go over here, one, how to check your answers with this. So let's do that first, actually. And then two, how you can save yourself some of the pain of the computations by doing stuff on Sage. Okay, so here we are in a Sage window to check this answer. So the first thing you got to do is, if you're saying that this function y of t is a solution, we got to plug it in like so. 2 times e to the negative t times cosine of t, yada yada, until you get to the 3 times sine of t. And by the way, this isn't just good for checking your answers, but you can imagine if this was the real world sort of problem, you might want to know what a graph of this looks like, so you can make a graph. And if I made a graph of this just to see, and I noticed it kind of looks just like a regular sine or cosine, it seemed like the parts with the e to the negative t must be getting pretty small pretty quick. So I just also plotted it next to this one here, which is just the negative cosine t plus 3 sine t, and you can see that they're almost the same after like t equals 2. They get really close to each other. So anyways, but what we really want to do is check the answer. Got a little sidetracked there. So we're trying to see if that y of t function I defined is a solution of the original problem. And the original problem was the differential equation that said y prime prime, which looks like this in Sage. The derivative of y with respect to t with an extra 2 there to be the second derivative, plus 2 times y prime, which looks like that, plus 2 times y. And we want to make sure we get 5 cosine of t plus 5 sine of t. And it's thinking about that for a moment here. Oh, it wasn't really thinking about that. I just didn't press the right button. Okay, there's the answer. It is 5 cosine of t plus 5 sine of t. And from there, we also want to make sure it satisfies the initial conditions. So if I want to make sure that y of 0 is equal to 1, it is. And the derivative of y with respect to t plugged in at t equals 0 should become 5, hopefully. Oh no, it should become 2. Yeah, y prime of 0 is supposed to be 2. Very good. Okay, so that's just checking your work using Sage. Now, how would you actually solve this problem if you wanted to use Sage to help you along with the computations? Well, one place where one thing you could do, I'm going to say, is for the method of undetermined coefficients, let's just say that a and b are variables. And define the original guess, let's call it yp, that thing we were guessing at, as a times cosine of t plus b times sine of t. That was the original a cosine t plus b sine t. And then based on that, that function yp now, we can put it yp is now really a regular old function of t, and Sage doesn't really know the difference between the variables a and the variable t. So by the way, if you did want to do something like take the derivative of that yp with respect to a or something weird like that, you could, and it will give you that partial derivative. But that's not what we really want to do here. What we want to do is plug in this yp into the differential equations so that we can determine the coefficients a and b. So to do that, you could just take yp prime prime which is actually going to look just like what we had here. Okay, sorry about the weird editing. I got interrupted the other day by a knock on the door, and I haven't been able to get back to it for a couple days. So anyways, here's the rest of the steps to work out this problem using this method. So I'm defining a function of t and also of a and b called the ls for the left side of the original differential equation, the y prime prime plus 2y prime plus 2y here, with where yp was just defined to be before where we were a cosine of t plus b cosine of t. So anyways, you have this function that has these three variables a, b, and t, and then I just define the right side to also be right side of t equals 5 sine of t plus 5 cosine of t. And we want to make the right side and the left side be the same function. So here's the step you can do that will save kind of a lot of work, so you don't have to go through working that all out on paper yourself, the way I was, or saving some of the steps here. So you can just write solve left side with t equals 0 equals right side with t equals 0. So that's leaving a and the b as variables on the left side. I can actually see what that looks like if I just write out show that equation here. I'm going to copy this, put that in there. Oh, and I have an extra brace there. That's going to be the equation a plus 2b equals 5. And then the other equation that it's solving, when you plug in pi over 2, is going to be the negative 2a plus b equals 5. So plugging in t equals 0 and t equals pi over 2 is essentially making it, well, t equals 0 makes it so the sine of 0 part is 0, and that's the first equation that gives you the coefficients of cosine. And plugging in pi over 2 makes it so cosine is 0, and we're just getting the coefficients of sine. Anyway, so solving that equation also gives you a equals negative 1 and b equals 3. Now let's go over how to do this bit here using Sage, where we try to find the C1 and C2 that makes this work. So I'm going to define the function y of t to be equal to this whole thing here. And here's what that looks like. I'm just saying y equals c1 times e to the negative t times cosine t plus c2, yada yada. You have to define c1 and c2 as variables first. And here's what that looks like. So to find out what c1 and c2 are, I'm going to do another solve function, kind of like before. But we're going to solve it with a system of equations for the variables c1 and c2. But the system of equations is going to be this. First, we're going to have the y of 0 equals 1. Here's what that looks like. Y with t equals 0 plugged in should be equal to 1. And then also y with t, the other one is the derivative with 0 plugged in. So that's going to look like this. The derivative of y with respect to t with t equals 0 plugged in, that result should be equal to 2. And that is now the system of equations that gives you these initial conditions that we're trying to solve for C1 and C2. See what we got. Hopefully I didn't make any mistakes here. Always a little nervous when it's thinking for too long. Oh dear. Oh, there it is. C1 equals 2, C2 equals 1. Took, why does it say it only took 0.011 seconds? Maybe I just have a slow internet connection. Okay, so anyways, those are some commands you can use with CoCalc to save yourself some headaches and check your answers. Different ways of going about these problems. You could also use your own imagination and do things your own way too. But yeah, it's a good idea to save yourself some of the drudgery of writing with these problems and do some of it with the computer. All right, see you next week.